F324 January 2012 question 3. This question's all about a disorganized technician who can't really keep his store cupboard in order, but the technician thinks that he's got a bottle of Pentan 2-one, Pentan 3-one or Pentanal. And what we have to do is describe a series of chemical tests to confirm that the bottle actually has a ketone in it. So include appropriate reagents and any relevant observations. So appropriate reagents, relevant observations. I would also, in this question, make sure that you get conditions in as well. You never can be quite sure what they're going to put on the mark scheme. Here you definitely want reagents and observations, but I suggest that you get down some conditions as well. So take a moment to think what you would answer. Here we've got add 2,4-dinitrophenohydrazine, 2,4-DMPH, either is fine. That will give your orange precipitate or your orange crystals, and that's for your 1 mark. Then you can say, well, that tells me I've got a carbonyl, but I'm not sure whether it's an aldehyde or a ketone. So my second chemical test, you add the Tollens reagent, and here I think it's important to say that you're warming your Tollens reagent. So you warm your Tollens reagent, warm water bath, and if it's a ketone, you get no silver mirror. An alternative to saying that, you've got your 2 marks if you've done that second part as well. An alternative to that is, of course, that a ketone will not oxidize further. So if you added potassium dichromate, acidified potassium dichromate, you would not get that color change from orange to green. So that would be another way of doing it. Part 2 then, describe how the technician could use the products of one of the tests to show whether the bottle contains Pentan 2-one or Pentan 3-one. So quite important bit here is describe how the technician could use a product. So here, use the products of one of the tests. So product one of the tests is not going to use the silver mirror. It's going to use the orange precipitate, the orange crystals, to show whether the bottle contains Pentan 2-one or Pentan 3-one. And this should not involve spectroscopy. So we're looking for a method to identify between particular ketones using our orange precipitate. So then that we have, of course, precipitate should be recrystallized to purify it, but there was no mark for that. But I do suggest that's one of, because it's one of your 3 bullet points normally for this type of determination between different ketones or between different aldehydes from your crystals. You initially recrystallize to purify it. You then measure the melting point of the crystals, and it must be melting point. Very important. People often get confused with that. Say boiling point, that will not get you the mark. It must be the melting point. And then finally compare the melting point to known values or to tabulated data to get to determine whether you've got the boiling point of your derivative of Pentan 2-one or your derivative of Pentan 3-one. Here at the start of part B, they tell you that you're going to use 3-hydroxypropanoic acid, and they tell you a little bit, quite an interesting little starter about how where it's produced from sugars in corn and how it's a green starting material for synthesis. However, that is not really important for your question. The question's giving you 3 synthetic routes for converting your 3-hydroxypropanoic acid into different polymers. And essentially, they're giving you the flow scheme and you've got boxes to fill in. So part I in the boxes below gives structures of the organic compounds formed. Here, since it's structure, give the structures. It doesn't say structural formula, displayed formula, skeletal. So you've got a free hand as to how you want to draw these, but they must be unambiguous. It must be clear where all the bonds are. So for our first synthesis, it's quite a nice one. With this one, we've simply got a straight polymerization. We're looking for one repeat unit. So here, the key thing to note, you've got your carboxylic acid, so it's the OH from the carboxylic acid that will come off, and the H from the alcohol that will be lost. And that then, if you take that H off and that OH off, that gives you your repeat unit. Of course, if you had two of these, then the OH from this end of the molecule would bond with the C double bond O from the other end in a row. Synthesis 2 is more of a tricky one. So synthesis 2 here, we've got a situation here where we've got elimination of H2O. So here we're going to lose one H and the OH. This is an AS reaction of 322. You eliminate water, OH from one carbon, H from the other carbon, so that you form a C double bond. C, you've lost water from that molecule, therefore elimination. Then we have a reduction. Now, we've got a reduction here of a carboxylic acid. We have said in our spec that we do not need to know how to reduce carboxylic acids, in the sense that we do not need to know the reagent for it. Sodium borohydride, which we use to reduce ketones and aldehydes, is not a strong enough reducing agent for carboxylic acids. So we do not need to know what or how this reaction occurs. It says though that it's reduction, so you're thinking, hang on a second, I don't know how to reduce a carboxylic acid. But shift to the end of the scheme here, and we have C2, CH2OH. We've produced an alcohol. The polymerization that's occurred, notice now from here, from elimination, we formed a double bond, which is here no longer there. And notice that this carboxylic acid group has become a CH2OH. So this gives us the clue. It's this that's the key piece of information. If you realize that this double bond has gone, we've got an addition, polymerization occurring. This is one of the groups. So my carboxylic acid must have been reduced to an alcohol. Spot on there the deliberate mistake. I am missing here, I'm short of a bond, aren't I? I'll put that H on there. So you can see here I've got my 1, 2, 3, 4 groups. I'm going to break my double bond and give it wings to produce my polymer. So here we've got a reduction. They've given us the answer to that question. It's not on our spec, but they've given us the answer. You don't need to know the reagent for it. Normally, we do not reduce carboxylic acids with sodium borohydride. In fact, carboxylic acids cannot be reduced by sodium borohydride, which is the one that we've got on our spec. Over the page to synthesis 3, we've again got this case of reduction. So we've still got our carboxylic acid and our OH group, our alcohol group. So oxidation, we can't oxidize the carboxylic acid. We can oxidize the OH group. Now we're going to fully oxidize that OH group to a carboxylic acid, as we was, because if you look down your page now, if you're looking at this with your paper, you will see that we've got to join both of these products into a polymerization. So we need to have both of these as carboxylic acids, and then through the reduction we again, from what we've learned in synthesis 2, that the carboxylic acid can be reduced to an alcohol, we're going to turn this into an alcohol again, so that we have our case for our polymers. So here we have the resulting from the reduction. We've got our two alcohol groups. From oxidation, we've made our alcohol into a carboxylic acid. So now in this question we've covered condensation reaction, where we've got a single monomer with an alcohol and a carboxylic acid which join together. We've got the condensation where you've got two different types of monomers, each with two of one type of functional group which join together. And we've also had that addition reaction, haven't we, where the double bond is broken. So here in this final synthesis then, we're putting these two together. Again, the important thing is to note that here we're going to lose the OH. Here, sorry, on the alcohol we lose the H, on the carboxylic acid we lose the OH, and again we get that bond between the C double bond O of what was the carboxylic acid and the O of what was the alcohol. So here it asks us to draw that as polymerization with, again, I think one repeat unit. So one repeat unit, notice I've taken the H off the alcohol there, as that's continuing to be part of the polymer, but we're just showing one repeat unit. There we've got the new ester bond that we've formed by taking the OH off here and the H off the alcohol. And again, we've taken the OH off the end of that carboxylic acid, because that will continue on with one repeat unit. Remember, when you're doing this type of polymer, you have water coming off, and you have 2N plus 1 H2O, which are formed because you get a water coming off at each of these linkages. The final part of the question then just rounds up. It just wants to tell you or ask you to check whether you've understood what each of these syntheses are in terms of polymerization. So state the type of polymerization taking place in each synthetic route. So the first one, condensation, we had our single monomer with an OH and a carboxylic acid, which same monomer joined with the same monomer, losing water. We've got addition because we had that double bond breaking, and then finally condensation because we had two different types of monomer forming that ester linkage.